Work is the transfer of energy by force along a displacement. While this generally means something is moving, there are some exceptions. Inertia doesn't count, and if there's no displacement, there's no work. The equation for work is force times displacement, and the units are in joules or Newton meters.
With work, the direction is important. Just because work is being done in the horizontal direction doesn't mean work is being done in the vertical direction. For example, moving an object forward doesn't mean I've done work upward or against gravity. If I do work in the opposite direction as my motion, then I'm doing negative work. I'm removing energy from my system, and it's slowing down.
If I lift something up, I'm adding work in the positive direction. But if it falls, the gravity has done negative work, and at the end my displacement is zero, and my net work is also zero. If I carry something, no work is being done on the object. This is because whatever forces are on the object, there is no force in the same direction as the displacement. There's no meaningful friction in the horizontal direction, and there's no acceleration. There's no additional energy. So there's no work.
One way to think of whether or not work is being done is if there's a change of energy at the end compared to the beginning.
If we drag an object along the ground, we have to add energy in order to overcome friction. We add energy via a force along a displacement. In other words, work.
Consider an object on a frictionless surface. Once the object is moving, it will continue moving forever. We don't count this displacement as work because we're not adding any force or energy, just like if we were carrying the object. If we want to calculate work, it's force times displacement. In this case, it's mass times acceleration due to gravity times the height. This is also the equation for potential energy. This makes sense since work is a transfer of energy. In this case, we're adding potential energy, so the two equations should be identical. For example, if a 100 kilograms boulder is rolled up a 60-meter hill, how much work is done? Work is force times displacement, which is mass times the acceleration due to gravity times the height, or 100 times 9.8 times 60, which equals 58,860 joules. How much work does a 70 kilograms man do if he climbs 3 meters up a ladder? He does 70 times 10 times 3 or 2,100 joules.
The work-energy theorem states that the net work on an object is equal to the change in its kinetic energy. Work can also apply to potential energy, but potential energy can mean a lot of different things, so it depends a little bit on how you apply it. A 600-kilogram car accelerates from 5 meters per second to 20 meters per second. How much work did the engine do? There are several ways to solve this, but the easiest is to use the work-energy theorem and calculate the change in kinetic energy. The change in kinetic energy is half the mass times the final velocity squared minus the initial velocity squared, or 0.5 times 600 times 20 squared minus 5 squared, which equals 112,500 joules. A 300-kilogram car is stuck in the mud. The mud has a coefficient of friction of 0.4. A tow truck wants to accelerate the car at a rate of 1 meter per second squared for 10 seconds. How much work did the tow truck do? In this problem, we need to account for the force of friction. We calculate this as coefficient of friction times the mass times the acceleration due to gravity, or 0.4 times 300 times 10, which equals 1200 newtons. The force required to accelerate the car is 300 times 1. Added together, the net force is 1500 newtons. The displacement can be worked out using displacement equals 1/2 times the acceleration times the time squared, or 0.5 times 1 times 100, which equals 50 meters. Adding both values to the work equation, we get 75,000 joules. To summarize, work is the transfer of energy by force for a displacement. The equation is work times force times displacement, and the units are in joules. Thank you for watching, and I hope you found this helpful.